At this stage, it's helpful to contrast the geometric approach with the algebraic approach. Because as I mentioned at the very outset, in general, we can't solve a typical nonlinear equation algebraically. But let's suppose that we could, and let's see what we can learn in the simplest example, or in a generic example where we can actually solve the equation of motion analytically, and compare what we learned from the algebraic solution and the geometric approach. So let's take as in our example the following equation of motion. X dot is equal to Rx1 minus x. This equation is known as the logistic growth equation, and when x is very small, we see that x dot is positive, if I can forget about the nonlinear term. And then when it gets close to 1, then the growth of x stops. And in fact, we can see immediately that x equals 1 is a fixed point, and also x equals 0 is a fixed point. Fortunately, in this particular example of a simple quadratic nonlinearity, the exact solution can be obtained easily. And so let me just leave that as an exercise for the student, but let me write down the exact solution. The exact solution is this. X of t is equal to x of 0, e to the rt, divided by 1 plus x0, e to the rt minus 1. It looks like everything is clear. When t goes to infinity, the exponential in the numerator blows up, the exponential in the denominator blows up at the same rate, and it looks like the x naughts cancel, and so it looks like x of t is approaching 1. But this simple solution contains a gotcha. If you're not careful, you can get fooled, because in fact, the asymptotic behavior depends on the value of x of 0. And so it turns out there's two possible behaviors. First of all, if x of 0 is greater than 0, the numerator is blowing up exponentially, the denominator is also blowing up exponentially, and notice that the second term in the denominator is always positive, so we don't have to worry about the 1. And so in this particular case, we'll just get x naught e to the rt divided by x naught e to the rt. We can forget about the 1 in the long time limit, and so we get that x of t goes to 1 for t going to infinity. However, and here was the gotcha, which is that if you weren't careful, you might miss the fact that if x0 is less than 0, then something else different happens, because when x naught is negative, then in the denominator we have 1 minus something, and that something is growing exponentially in time. And so there'll come a critical time at which the denominator is equal to 0, which means that the function is actually blowing up. And how is it blowing up? It's actually blowing up to minus infinity. So if x naught is less than 0, then what we're going to find is that x of t goes to minus infinity. And this happens when the right-hand term in the denominator is equal to minus 1. So when e to the rt minus 1 times x of 0 is equal to minus 1. Or the blow-up time, t is equal to 1 over r logarithm 1 minus 1 over x of 0. It's not evident from the solution itself, but there is two different types of long-time solutions, one which is perfectly rational and you approach 1, and the other one with an exponential blow-up. But let's now contrast this algebraic solution, which contains this gotcha, with the geometric approach. Let's now look geometrically at the same problem. And all we do in the geometric approach is that we plot x dot as a function of x. It's easy because this is a simple quadratic function, and so plotting x dot as a function of x, it starts out at x equals 0 equal to 0. It starts off with a slope r, and so it's rising, and then it's an upside down parabola. When x is equal to 1, it hits 0 again. So this is our function, x dot is a function of f of x. And we can immediately understand the dynamical behavior without having to think all that carefully. Wherever the function goes through 0 with a negative slope is a stable fixed point. Whenever the function goes through 0 with a positive slope, it's an unstable fixed point. To the left of the unstable fixed point, x dot is negative, and so we flow to the left. When f of x is positive, x dot is positive, we flow to the right. And again, to the right of the stable fixed point, the flow is to the left. And so we can infer right away that the stable solutions, or the long-time solutions, are either we flow to x equals 1, and that'll happen in the basin of attraction of x equals 1, which is any x0 which is positive. And if x0 is negative, then we're in the basin of attraction of minus infinity, and we flow to minus infinity. So with very little work, and with very intuitive work, we can infer the long-time solution of this nonlinear system. Now, this example was cooked up so that we could actually solve the nonlinear problem fully and see the algebraic solution. in general, we don't have that luxury, and so it will turn out that the geometric approach is absolutely essential to understand the dynamics of one-dimensional systems.